So the title of today's talk is Perovskites, Ancient Structure, Modern Applications. And the aim of this presentation is to really introduce Perovskites to you and hopefully show you how remarkably versatile materials they are and some of the applications they have, and specifically the green applications and the energy saving applications or the energy producing applications they may have, and how these can be implemented in real world applications with some further research and development. So firstly, onto the agenda of today's webinar. So I'll start by giving a quick introduction to Goodfellow and explain a little bit about who we are, what we do, and our history. I'll then move on to the topic of today's presentation, which is Perovskites. I'll go through the history, discovery, and origins of both the mineral Perovskite and then the family of materials named Perovskite before describing the Perovskite structure in some detail. I'll then discuss the current and potential applications of Perovskites, which are quite wide-ranging, before zoning in and concentrating on three current areas of intensive research and development. Towards the end of the presentation, I'll show a short video showcasing us here at Goodfellow before finishing off with some short conclusions. So firstly, the introduction to Goodfellow. So Goodfellow is a global brand with over 70 years experience facilitating scientific innovation and research. So we were originally established in London in the year 1946, and we are currently based in Huntingdon, just outside of Cambridge in the UK. We are a global company with operations in France, Germany, America, China, and we are able to supply metals, alloys, ceramics, glasses, polymers, and compounds, of which Perovskites come under the category of compounds. We have over 70,000 catalogue products to choose from, and most are subject to free delivery within a short period of time. We also offer a range of processing services in-house and have a team of scientists and engineers that are able to help us meet our customers' research and innovation needs. So that brings us on to the topic of today's presentation, Perovskites. The Perovskite is actually the name given to the oxide mineral calcium titanate, CaTiO3. I want you just to pay attention to this formula whereby we have two cations, calcium and titanium, and three anions, so O3. So this is the general formula of a Perovskite. So you can see calcium titanate in these top two images as a black cube-shaped type lump. So this mineral was first discovered in the Ural Mountains of Russia by the German mineralogist Gustav Rose in the year 1839, and this is the gentleman shown on the bottom left. So he identified many minerals new to science, including Perovskite, during his distinguished career. And because of this successful career, by the time he discovered Perovskite, he already had a mineral named after himself, and this is the rose-coloured mineral named roselite. Therefore, when it came to naming the newly discovered calcium titanate, he named it in honor of his friend, Russian mineralogist Lev Perovsky, hence the name Perovskite. So following the discovery of calcium titanate and the characterization of its structure, a whole family of materials with the same basic crystal structure as calcium titanate were discovered. So then this whole family then adopted the name Perovskite, and the structure was known as the Perovskite structure. So since I mentioned Perovskites have a related crystal structure, I thought I'd introduce what I mean by the term crystal structure before moving on. So a crystal or a crystal structure is a body consisting of a 3D periodic long-range ordering of either atoms, ions, or molecules. So an example of a crystal structure can be seen in the image on the top right. In this image, I hope you'll be able to see a periodic repeating pattern of atoms. So I've put the laser pointer on there, a green sphere, and you can see around it there are four purple spheres. Again, if we just go to a different one, we have a green sphere with four purple spheres surrounding it. So this is a periodic repeating pattern. And for those that are interested, this crystal structure here is actually the crystal structure for sodium chloride, otherwise known as table salt. So given this periodic ordering, a structure such as that in the top right can be simplified into what is known as a unit cell. Now, the unit cell of this structure is seen in the bottom image. So a unit cell is the smallest repeat unit that can be used as a building block to make a 3D crystal. So if we put this unit cell, start putting it side by side and on top of each other in all directions, we start to build up the 3D crystal in the top again. But all the information we need to build up this crystal is contained within this unit cell. So a unit cell is based on lattice points. This is the position in which, within this unit cell, the probability of finding an atom or ion or molecule is at its highest. And it is these positions that determine the shape of the unit cell. For example, in the unit cell we have on the screen now, this is known as a face-centered cubic. And this is because the purple spheres we see are located on the points of the edge of the cube and a purple sphere on the face of the cube. So this is why this is known as a face-centered cubic. But all the unit cell shapes and sizes are known. And this brings us on to what is known as the Bravais lattices. So these are simply the different shapes of unit cells that are available to crystal structures. There are actually 14 Bravais lattices, and these cover all crystals, not just perovskites. Any crystal structure will adopt one of these 14 unit cells. These unit cells can include names such as triclinic, monoclinic, orthorhombic, tetragonal, trigonal, and cubic. And the one from the previous slide is this one here, cubic with face-centering atoms. So since this webinar is about perovskites, I won't go into too much more detail about crystal structures. I just wanted you to be aware that different shaped unit cells are available, and these shapes can play a very important role in the properties of a material and the properties of materials such as perovskites. And I'll come on to how the shape of these unit cells is important in properties when I come on to the applications of perovskites later on in the presentation. So now I've introduced crystal structures and unit cells, and I want to move on to the perovskite structure. So as I mentioned at the beginning of the presentation, perovskites have a general formula, and this formula is AbX3, and we already came across calcium titanate as one example of this. So calcium is your A, titanium is your B, and then O3 is your X3. So calcium titanate matches this general formula AbX3. So on the right-hand side of this page is an image of the perovskite unit cell. So the simplest repeat pattern that could be used to build the perovskite structure. So we have our perovskite unit cell. Now we call this the ideal perovskite unit cell, reasons which will become apparent in a few slides' time. So within this unit cell, right at the center, we have this green sphere. Now we call this the A site, and this is where this is a large 12-coordinate A site. By this we mean it bonds to 4 oxygens in the plane, or 4 Z sites in the plane, and 4 above and 4 below. So surrounding this large 12-coordinate A site, we have these 8 purple octahedra. Now these purple octahedra are made up of the X sites that are said that the A site was bonded to, and this makes this octahedra pattern. Now within this octahedra, we have what is called our B site. Now this B site is a bit smaller than the A site, and it is only 6 coordinates, so it bonds to 6 of the what is on the A site, surrounding it 2 above and 4 in the plane. So that is simply the structure. Now what kind of compositions can this structure adopt? Well, the A site usually contains, because it is large, usually contains large cations, such as calcium 2+, strontium 2+, barium 2+, and that is the oxidation state of the cations, but can also contain 3+ cations such as lanthanum or other rare earth cations. And because the B site is smaller, the B site contains smaller things such as 4+ transition metals, and these can be titanium, iron, zirconium. But again, this can also contain 3+ cations, such as iron 3+, rhodium 3+, chromium 3+. And the atoms that are on the X site are usually a 2- ion, such as oxygen. Now, this is the most common oxide. Atom is usually oxygen, but things such as the halides can go on this site, such as iodide, which we will see an example of later in the presentation. I've mentioned the charges of the atoms there. If we go back to the general formula AbX3, if X is normally oxygen, oxygen has a formal charge of 2-. So we have 3 of these, so we have a -6 charge. Therefore, your A and your B cation have to have a charge of +6. So therefore, if your A site is a +2, your B site must be +4 to add up to a total of +6. Or if your A site is then a +3, your B site needs to also be +3 to add up to a charge of +6. But again, this isn't always the case. Sometimes the charges don't balance, and this leads to defects in the structure or vacancies in the structure. And this can play a very important role in the properties of perovskites. So that was the ideal perovskite structure, but the structure can vary. So on the right-hand side of this slide, we have the ideal perovskite structure that I just explained on the previous slide. So for the first time, I'll actually name this. So this is actually the structure of strontium titanate. So strontium on the A site, a big 2+ cation, titanium, a smaller 4+ cation on your B site, and then the X site contains oxygen. However, a large number of simple perovskites display distortions from the ideal structure, and that can be seen in the image on the left. So this is actually the structure of calcium titanate, the original perovskite mineral. So again, in this one, we have calcium on our A site, we have the smaller titanium on our B site, and we have oxygens on our X sites. And as you can see from the image of calcium titanate here, it looks ever so slightly different to the ideal structure. And this is because it is tilted slightly. You can see here that the bonds going through the strontium titanate structure are perfectly straight, perfectly 90-degree angles, but in calcium titanate it's no longer straight, and this is because these what are known as BX6 octahedra have tilted. And this happens because the octahedra are connected to one another. They all share an oxygen atom at its point, so if one tilts, the one above it has to tilt, because they share an oxygen atom. So this is just one example of a distortion in perovskites, but they can be seen by a few methods. So you can have rotational tilting of the octahedra, as I've just described in calcium titanate. You can have distortion of the BX6 octahedra, and by that I mean you can either squish it, so the 4 bonds that are in the plane of the atom come in, and the 2 above and below elongate. That is one way that these BX6 octahedra can be distorted. Or we can also have distortion of the A and B cation polyhedra, although that is a bit less common and less important for the properties I will discuss later on in the presentation. So now I've described these distortions, you may well be thinking, well, why do these distortions take place? So I'll explain this in a bit more detail. So it is simply to do with the size of the A and B cations, or rather the difference between the size of the A and B cations. So in the ideal structure, everything is perfectly balanced. The size of the atoms and the bond lengths and the bond angles are all ideal. So that is strontium titanate we saw on the previous slide. But now imagine that if that A cation gets smaller. So this A cation, as I said, is coordinated to 12 oxygen atoms around it, 4 in the plane, 4 below and 4 above. And these oxygen atoms make up the BX6 octahedra. So if this cation on this A site got smaller, because the oxygen cation bond length doesn't matter on the cations, stay pretty much similar. If the A cation gets smaller, the oxygen ions that it's bonded to need to come in slightly. And when it does this, it pulls on those octahedra and it tilts them. And the opposite is also true if the cation size gets larger. So if you put a larger cation in that A site, it pushes those oxygen atoms out a little bit, again, distorting the structure, moving those BX6 octahedra. And what important is here is that these distortions play a very important role in the property of materials. And this is called the structure-property relationship. Because if a structure gives you a specific property, you can then target a specific structure to give you a property if you know what you're looking for. So because of this, research developed a mathematical equation to give a number called the tolerance factor that links the cation sizes in the structure to what structure would be predicted. So the table here on the bottom left shows the tolerance factor for different perovskites and the structures that they can adopt. So this actually makes a bit of sense if we look at the cation size for the titanates on this list. So for example, I've said strontium titanate here is the ideal perovskite, and this adopts the cubic structure and it has a tolerance factor close to 1. Now, if we make swap strontium out in a titanate for something that is smaller, such as calcium, mathematically we get a smaller tolerance factor, and this predicts a change in structure toward rhombic. And conversely, if we swap strontium out from the cubic with a tolerance factor of 1 to the bigger barium, again, the tolerance factor then mathematically goes above 1. And again, we predict a different type of structure from cubic. And what is probably the most important point I want you to take away from this slide is that if these distortions can be controlled and predicted, specific properties can be targeted, which is very vital for the research development industry because it saves time, it saves costs, because instead of just randomly saying, I will make a perovskite, you could target which perovskites and which mix of cations you want to give you a specific structure, which can have specific applications. So that was the simple perovskite structure, but to add another layer of complexity, layered perovskites are known. So now these layered perovskites contain the perovskite structure in small blocks, which are then separated by another layer before another block starts. And quite often, these new blocks are offset from the previous block by a half. So these layered perovskites are shown here. So we have the D and Jacobson structure. So you can see your perovskite block here at the bottom, and you can see it's separated from the perovskite block above by a layer of another structure. And the same can be said in this, what is known as Ruddleston Popper. You have your perovskite block layered by another layer. And again, in the Aurelius, your perovskite block separates from the next perovskite block by another layer. So these layered perovskites still have the same compositional variety as normal perovskites. So you still have you can still put strontium, barium on the A side, titanium, iron, zirconium on your B side. Your anion can also change. And these almost have applications in almost all the same fields as the standard perovskite. So I don't want to go into too much more detail about these perovskites because the structures can get a bit more complicated, but I just wanted you to make you aware that they do exist. I think at this stage, it was also be a good time to discuss how perovskites can be synthesized before moving on to discuss their applications. So the simplest way to produce a perovskite is known as the solid state method. So this method requires mixing the powdered oxides of the cations you want to be present in the correct ratios. So for example, if you wanted strontium titanate, you would mix strontium oxide and titanium oxide together in the correct ratio. And once you've mixed those powders together in the correct ratio, you can either press it into a pellet or leave it as a powder and heat it to a very high temperature in air to temperatures above 1,000 degrees. So this method often produces single-phase perovskites, but the downside to this is because of the method, they generally have very large particle sizes, and this can be something which can be detrimental to the properties of the perovskite. So other methods to produce perovskite have also been used that can produce smaller particles. So these include hydrothermal methods, and this is a method where a solution of your desired cations can be heated in what is known as a hydrothermal bomb. We also have a sol gel method where the cations are trapped close together in a gel, an organic gel, before being heated, and this organic substance is burnt off. And because both of these solutions I just said are not solid based, but are solution based, lower temperatures are required to make the reaction happen, and also the particles produced by the reaction are smaller. Another method of producing perovskites, and especially these layered perovskites that we still see here, includes using sputtering targets in equipment such as a PLD or a PVD, so physical vapor deposition. And what you can do is you can grow these layered perovskites layer by layer using specific targets and specific compositions of targets. So here at Goodfellow, we do offer our perovskites as sputtering targets also to make these layered perovskites. So far, all I've talked about is the structures of perovskites and the compositional variety they can have, and how the compositions can distort the structure. So now it's time to turn our attention towards the properties and applications of perovskites. So this is probably the most important part of the presentation. So here I show several areas in which perovskites can be employed, and I'll go around each one individually and just explain very little about the application of why perovskites are good for this, or why perovskites are being researched for this application. So first is sensors. So sensors detect the movement or pressure of something, or even the pressure of a gas or molecule, and give a signal to the user that either this pressure is there or this molecule is there. So specifically for pressure and movement sensors, perovskites have a property called piezoelectricity, and this is where they can produce a voltage in response to a physical force. And I'll go more into detail of this in the coming slides, but because of this property, perovskites are very actively researched for their sensing properties. The next one round on the circle is thermoelectric applications. So a thermoelectric is a material that can convert waste heat into an electric current. And this area has received a lot of research in recent years to the desire of conserving energy. So if you have a process that makes a lot of heat, for example, a car engine, and that heat is just wasted, we are wasting a lot of energy. So perovskites are thought of as promising thermoelectric materials to capture this energy and convert it to electricity, so we're not wasting as much. Perovskites also have applications in lasers. Because of the compositional flexibility on the B site I've mentioned, atoms such as europium can be put on this site. And when a perovskite has europium in its structure, for example, and this perovskite crystal is then hit with energy, photoluminescence can take place, and the crystal can emit light at a specific wavelength. And because perovskites can be compositionally varied, you can vary the wavelength of laser light that is emitted, which is really important for some laser applications. The next one we have is catalytic applications. So catalysis is the process of increasing the rate of a chemical reaction by providing an alternative pathway. Now again, because perovskites have this B site and a lot of different atoms go on this B site, the B site can act as an active site, and this is the place where a reaction can take place. So perovskites are thought of as good catalysts because this B site can be tuned to a lot of different catalytic processes. And again, this is one of the areas I'll focus on in the coming slides, so I'll go into more detail about that later. So perovskites find applications in battery technology, and these are especially the layered perovskites, as I mentioned on the previous slide. Because of these layers between the perovskite blocks, lithium ions can be put in between these layers, and this finds applications in lithium-ion batteries where you need high movements of lithium throughout a structure. So perovskites are thought to be useful in lithium-ion batteries. Next, we have fuel cells, and specifically solid oxide fuel cells. So these cells convert chemical energy direct into electrical energy. And perovskites, because of their structure, they can be investigated for the use as both cathodes and anodes in fuel cells, which is another really interesting emerging technology. And the final one we have here is photovoltaic applications. So this is an application I'll talk about a bit later, but solar panels need materials that can absorb visible light and convert this light into electrical current. And perovskites, because of their composition and the transition metals you can put on their B sites, can absorb visible light. So given the correct composition, perovskites can be used in photovoltaic applications to absorb visible light and create a current. And one thing I really want to point out here is you may notice a theme throughout all these applications. So photovoltaics, thermoelectric, catalysis, batteries, fuel cells. The majority can be considered green or environmentally friendly applications. So they use light or waste heat to create electricity or to store electricity to use at times when are desired. perovskites find a lot of applications in really green, environmentally friendly sectors. So now onto the research fields in which perovskites are being investigated for potential uses. The first field I'll talk about are piezoelectric and ferroelectric perovskites. So first I'll discuss the origins of piezoelectricity and ferroelectricity and how the perovskite structure is so important for this. So on the left here on this slide, we have the ideal perovskite unit cell again. Although this is a slightly different view than the one we saw earlier, it is still a perovskite unit cell, except the A cation is on the corner this time and the B cation is in the center. But the important point in this image is to get that the B cation is right in the center of that octahedron. It's right in the middle. However, sometimes the cations can move from the center of this octahedron, as is shown on the right. See, this cation is now off center. And this can happen by a number of ways. It can happen by mechanical force. So if you compress the structure and put it under a lot of strain, the cation is forced to move from the center of that site, and it's forced to do this to kind of occupy its lowest energy state. It can also happen when a material is cooled to a specific temperature. Now, this usually happens well below room temperature, limiting any applications of if this happens way below room temperature, because for a piezoelectric crystal to work, you don't really want to be cooling it down to cryogenic temperatures. But maybe the most interesting way that this can happen is what is termed as naturally. And by this, I mean the cation is naturally off-center. You don't need to do anything to get it off-center. And this is normally the case when one of the cations in the structure has a lone pair. So this cation could donate its lone pair of electrons to the oxygen atoms near it. And then this causes the B site cation to move off-center of that octahedron to occupy its lowest energy state. Now, this is known as the stereochemical activity of the lone pair. Now, this stereochemical activity is actually the source of ferroelectricity and piezoelectricity in well-known and researched perovskites such as bismuth ferrite, BiFeO3, lead titanate, PbTiO3, and bismuth manganate, BiMnO3. And this is a good example of how you can use your composition to target a specific property. For example, if you know you can get this off-centering by having a cation with a lone pair, you will then target compositions where there is a cation with a lone pair if you're targeting this property. So at Goodfellow, we currently have bismuth ferrite as a sputtering target in our catalogue, and we also have lead titanate as both a sputtering target and a powder in our catalogue. However, we'd also be able to supply other such perovskites as both powders and targets on request. So the property of piezoelectricity and ferroelectricity comes from this off-centering. So when this off-centering takes place, more plus charge is actually in one side of this unit cell than the other, and this creates a dipole. So if we look here, because this black plus cation is closer to the top of the cell, there's now more plus charge towards this side of the unit cell than the bottom side of the unit cell. And this is what creates the property. So the two properties are piezoelectricity and ferroelectricity. Now, piezoelectricity is an electrical charge that accumulates in certain materials in response to an applied mechanical stress. And these perovskites need to be able to display this off-centering effect. Now, interestingly, and maybe more important for piezoelectric materials, they can also expand or contract in response to an electric charge being applied to it, as we can see in this image here. Now, this has really important implications in terms of the applications in which piezoelectric crystals can be used, more of which will be said on the next slide. Now, the second property is ferroelectricity. Now, this is a property that some perovskites can have, whereby there is a spontaneous electrical polarization. Now, this becomes because the cation is off-center naturally. Now, this spontaneous electrical polarization can be reversed by the application of an external electric field. So you can have your polarization pointing up, and then if we from outside apply an electric field, we can convert that polarization to be pointing down. And again, this property has real important applications when it comes to using a ferroelectric crystal. So now onto these applications. So for example, possible applications. So for example, a microphone. If you have a piezoelectric crystal in a microphone, it can pick up the vibrations from your sound, from the sound waves coming out your mouth. This is a stress on the atomic level. This creates a voltage in your piezoelectric crystal that can then go down the wire that your microphone is attached to a computer and convert this back to sound. A piezoelectric crystal can be used in an MRI scanner. For example, if you need to move someone ever so slightly within this scanner to get a better image, a piezoelectric crystal can be used. So if we from the outside apply voltage to the piezoelectric crystal, it can expand. And because this expansion is so small, we can control people ever so slightly within these scanners. Again, a piezoelectric crystal in an inkjet printer. A set amount of ink needs to be let out of the nozzle at a set amount of time. Now, if a piezoelectric crystal is there at the nozzle, say it is closed, we apply a voltage and we can expand that crystal and open it slightly, let out a bit of ink, take away that voltage, it closed back over, it can find an application in an inkjet printer. Again, a piezoelectric sensor can find an application in a car. So if a car engine starts vibrating too much, a piezoelectric crystal can pick this up, create a voltage, goes to the car's computer and tells the driver there is a problem. And again, a piezoelectric crystal in a balance. We can add weight on top of the crystal produces a voltage, and if the balance is set properly, it converts this to the correct mass. So there are 5 applications for piezoelectric crystals, and one of a ferroelectric is ferroelectric rapid access memory. Now, as I said, a ferroelectric crystal can be polarized up or down. And for anyone who knows how data is recorded as 1, 0, 1, 0, up, down, up, down. So if we can set specific crystals to up, down, we can then read this afterwards as stored memory. So these are some applications of ferroelectric and piezoelectric crystals, but currently most of these applications use quartz crystals. But researchers always look for new and exciting materials that can not only replace quartz, but also offer superior properties with a material that is not only more accessible in terms of price, but synthesis too. And Perovskites are one of these materials. So the ease of synthesis and the abundance of the elements that are in Perovskites make them very interesting for these applications. And one of the most widely researched Perovskites for these applications is lead titanate, which I said we at Goodfellow do have. And this lead titanate can be doped with zirconium, known as PZT, and this is what is used in these applications. So the second research field where Perovskites can find applications is in catalysis. So catalysis is the process of increasing the rate of a chemical reaction by providing an alternative pathway for that reaction. Now, this is most commonly thought of an organic chemical process whereby people add protons to things, but solid inorganic materials such as Perovskites find applications in catalysis too. Now, this is because, as I have said throughout this presentation, these sites in Perovskites can be compositionally varied. So a lot of different transition metals can go on that B site, and these B sites act as an active site. Now, an active site is where a reaction can take place. And it's because of the wide variety of cations and oxidation states available to these cations that can go on these B sites, Perovskites can be used in a variety of catalytic applications. Now, one of these applications is photocatalysis. So photocatalysis is the process of converting light energy directly from the sun into chemical energy. And one such process is splitting of water to produce hydrogen, and this hydrogen can then be used in fuel cells or cars as a green energy route. So catalysis can, and perovskite catalysis can be a very green application. Now, perovskites are good for this application, and especially photocatalysis, because they are what known as semiconductors. And semiconductors are materials that can conduct electricity through their band gap. Now, I'm show here an image of a semiconductor band gap. So you have a band here at the bottom, which contains electrons, and you have a band here at the top, which is empty. Now, these bands are separated by a specific energy, and this energy is about equal to that of visible light. So if your perovskite contains an element such as rhodium or chromium that can absorb visible light, you can promote an electron from the bottom band to the top band, and this is what makes it a semiconductor, and this is also what makes the catalysis take place. So examples of perovskite photocatalysts include calcium titanate, barium titanate, and probably the best performing is strontium titanate. And again, all these are available from Goodfellow upon request. So another catalytic process that perovskites can be used for is methanol production. Now this can convert waste CO2 captured from the environment into methanol to again be used as a fuel. So this kind of completes the carbon cycle. We burn fuel, we create CO2, put it into the atmosphere, we absorb that CO2 back, convert it back to fuel, and we use it again. So this can be considered as another way of perovskites being used in an environmentally favorable way. So just another note, the production method of perovskite in catalysis is vitally important when it comes to perovskites, because the B sites where the reaction takes place, you want as many of these to be exposed as possible. So you want a material with a very high surface area. And for a very high surface area material, you need small particle sizes. So therefore, you probably need to make your perovskite via some sort of solution method. And now on to the final research area I'll discuss is photovoltaics. So photovoltaics are a class of materials that are used in solar cells in order to convert light energy into electricity. Now this process requires a semiconductor material that exhibits the photovoltaic effect, and this effect is the generation of a voltage or electrical current in a material upon exposure to light. So as I mentioned with the catalysts, perovskites are semiconductor materials, and these can show the photovoltaic effect. And this is again why they can absorb visible light and excite electrons across its bandgap. And then when we excite these electrons, we can then use this to create an electric current. Now the perovskite on the right here, called methylammonium lead iodide, is one of the best performing perovskite materials for this application. And what you may notice about this perovskite is that not only is iodide on the X site rather than oxygen, it also has an organic molecule in the A site rather than a metal cation, as I have been repeatedly talking about. And again, this shows the remarkable versatility of the composition and structure of perovskites. Now, this perovskite here has a couple of disadvantages. Its stability is actually pretty low in light. So if you were to put this into a solar cell, it wouldn't last very long. And also it contains the toxic lead cation. So if this was to be upscaled and be really industrialized, there's a lot of toxic risk there. So extensive research is taking place to replace this with another perovskite. And for example, replacing the lead, which is a cation which has a lone pair, with another one which has a lone pair, such as bismuth, has been investigated for swapping this lead for bismuth in perovskites. And this is really an active area of research at the moment, try and improve the stability of perovskite materials in solar cells. And this is where Goodfellow being able to supply perovskites can really help and assist researchers in their goal. Being able to readily supply perovskites, which can be used in the lab within a matter of days of them ordering. So they can go from the shelf at Goodfellow to research within a matter of days and be used potentially in some of the applications I've just run through. So now, as to conclude, so perovskite is the name given to a whole family of materials that have the same basic crystal structure as calcium titanate. These perovskites include things such as strontium titanate, lead titanate, and the list goes on. They have remarkable compositional variety on both the A, B, and the C sites. And it's this wide-ranging compositions and then the structural distortions that happen that give perovskites their wide-ranging applications. And these applications can include things such as photovoltaics, as I described, sensors, catalysis, and thermoelectrics. And a running theme through these applications is that they are really green, environmentally friendly applications. And these are very intensive, active areas of research at the moment in order to benefit society, reduce greenhouse gases, and provide alternative energy sources. So perovskites are really interesting materials for these applications. So I think that is all for me for the moment. So I think we'll be able to move on to some questions. So the first question we have here is, can we find out the tolerance factor of other materials other than perovskites? Is yes. Please suggest how to do the same. The perovskite related materials, yes, there are tolerance factors. So for example, those layered perovskites, that you can get tolerance factors for them as well, and that'll predict the layering structure of those perovskites in those layered ones. Off the top of my head, I don't know the equation for those tolerance factors, but that is certainly something I'll be able to look into and be able to provide you with that information. I think they are readily available in literature papers, perovskite summaries. So I'll try and find that information for those layered perovskites if I can. So there's two questions here, how the stability of perovskites can be improved. The stability comes down to just how stable the structure is, how close to the minimum energy state you are. So the stability of perovskites can be improved by two methods. One is computationally. You can predict what energy the structure has. So if you make a perovskite that isn't stable, you need to look at what other structures are below that in the energy scale and synthesize those. And then again, this comes down to the compositions you can put on the A and B sites. For example, with the last one I showed, methylammonium lead iodide, it's unstable, but if you can swap that lead for something such as bismuth, it becomes a bit more stable. So these are fundamentally structural questions. The stability is related to the structure and the cations and composition of it. So in order to improve the stability, you need to really improve or change what cations are on those sites without diminishing the applications. Obviously, you don't want to change the cations, so you get a stable perovskite, but then it's useless in the application you're looking at. The next question is, why only B sites are active sites and not A sites? And again, I think this comes down to the composition. So a lot of catalysis is done using transition metals. So even if we take perovskite out of it, a lot of catalysis uses iridium, platinum, rhodium. They're very good catalysts. Now, these atoms we can put on the B site. These atoms don't go on the A site. So I think it's more to do with the composition of what's on the B site rather than it's the B site itself which makes them those active sites. So it's more to do with the fact that you can put rhodium, iridium into those B sites. So it's more the element that does the catalysis rather than the B site. Can you give an explanation of 2D perovskite materials? So these are rather, they're just thinner layers. So rather than a big crystal, you can deposit just thin layers of these materials, and these are what are known as 2D materials. So for example, the magnetic application of ferroelectricity, if you can just get one layer, you can really point the polarization in one direction for the 2D perovskites. And the last question here I've got is, does the change of oxygen in AbO3 bring out a major change? And is it possible? Changing from the oxygen to other anions such as iodine does really change the properties. So for example, in the last example, methylammonium lead iodide, if that was oxygen, it wouldn't be able to absorb light as readily. Now this is all to do with the overlapping of what is known as the electron clouds or the orbitals of those atoms. So this kind of gives what is known as the electronic structure to the material. So changing oxygen for other anions can change the electronic structure of your material and can really be tuned for specific applications. And we have another question that's just come in that says, since lead is toxic, how can we synthesize non-toxic perovskites? And well, that is just really switching out the lead for another cation. So as I've said, in methylammonium lead iodide, people have swapped out that lead for bismuth or copper. So if you don't want to make a toxic perovskite, you have to change that cation, and then research what cations can you swap it with. Will it maintain the properties? Will it not? Will it diminish those properties? Will it not? And obviously, this is where quite a large area of intensive research is taking place at the moment to try and make non-toxic perovskites for use in those photovoltaic applications. And again, we have another question that's just come in. What are the major challenge of perovskite solar cells? And again, the major challenge is really the toxicity of the current best performing, which is methylammonium lead iodide. That is a major challenge of these perovskite solar cells. So a lot of research is going into replace that lead, as I've said, with bismuth or copper. But also the stability for the methylammonium lead iodide is not that stable. It breaks down quite readily under visible and UV light. And obviously there's quite a lot of UV light that hits the Earth's surface. I think it's about 4% of our light is UV light. So if you put this in front of that light, it breaks down remarkably quick. And when I say remarkably quick, it may take a few weeks, but obviously you don't want to buy a solar cell and it not work after a few weeks. You want that to last 20, 30, 40 years. So that's the second major challenge, trying to find a perovskite material that not only has the photovoltaic properties in terms of capturing as much light as it can and converting it to electricity, but also those properties lasting a long period of time without the perovskite breaking down. So another question just came in. How can we find the structure of perovskites other than ABX3, e.g. A3, B2, X9? So other layered perovskites are known, and I think this formula here, A3, B2, X9, is a perovskite, I think, or a layered perovskite. So you could be able to find those structures in literature, in books. After this presentation, I'll try and find a diagram or explanation of that other perovskite structure for you and be able to send that over. So I think that is that for the questions. I've been through the list now, unless there's any more to come in.